Now, in this lecture, we introduce human capital to the research and development based growth model, and we show that in doing so, we can eliminate even the weak scale effect. This makes the model then more consistent with the empirical observations since the Second World War, when population growth and economic growth have rather been negatively associated. Now, this part is based on two papers, The Past and Future of Knowledge-Based Growth, published in the Journal of Economic Growth, and The Non-Monotonous Impact of Population Growth on Economic Prosperity, published in Economics Letters. We have seen in the previous lecture that the semi-endogenous growth framework eliminates the strong scale effect, but it introduces a weak scale effect. And this weak scale effect is also not supported by empirical evidence since the Second World War, because population growth and economic growth are rather negatively related but not positively. Now, the idea of how to get rid of this counterfactual prediction is that not the sheer number of people is what matters for research and development and DFB growth, but the stock of human capital in the economy that is available for research and development. So it's not so much the sheer number of people, but their education. Now, this idea is already mentioned by Roma and emphasized actually in his 1990 paper, because in the production function he has the stock of human capital and not the number of people, but it was not explicitly modeled. So there is no investment in education and there is no trade-off between how much you invest in education and how many children you have. And this trade-off is very well established in the family economics literature, where households derive utility not only from the consumption, but also from the number of children and from the education of each child. So there is a certain degree of altruism in the model. And then if a household has more children, then by means of the budget constraint of the household, it can invest less in education of each child, and vice versa. If more should be invested in education of each child, then the household typically has fewer children. That's very well established in the family economics literature, theoretically and also empirically. And as we will see in a framework of semi-endogenous growth, if we introduce this decision and if we introduce human capital accumulation, then we can get to the prediction at the aggregate level that population growth and economic growth are negatively related. To this end, we now consider aggregate human capital, denoted by H sub d, instead of the population size. The model is formulated in discrete time because that's easier to deal with the quality-quantity trade-off at the household side. Now, there are two dimensions of human capital, basically. The quantity dimension, that's the population size, how many people there are, how many scientists there are. That's still denoted by LT, so that's the production factor, labor. But there is also the quality dimension. This could consist of health, education, and so on and so forth. That's the human capital. And individual human capital is denoted by lowercase ht. Now, aggregate human capital is, by definition, the product of individual human capital with the number of people in the economy. And its growth rate is denoted by gamma sub h in the following. Now, this modification of the semi-endogenous growth model takes into account for human capital instead of the raw population size. And if we do all the calculations on the production side of the economy, we would get the result that the growth rate of per capita GDP now depends not on the growth rate of the population, but on the growth rate of aggregate human capital. That's the only difference to the semi-endogenous growth model, to the growth rate of the semi-endogenous growth model. Here we still have the same parameters as in the semi-endogenous growth model, the parameter related to the stepping on toes effect. So if this increases, the stepping on toes effect becomes weaker, and the intertemporal knowledge spillovers. So if they increase, then the denominator gets smaller, and the growth rate would, ceteris paribus, increase. Now, while the production side is a rather straightforward extension of the semi-endogenous growth model, and it follows in a quite straightforward way that the growth rate of per capita GDP should be the one that I've shown you on the previous slide,
The consumption side, the household side, changes quite a lot. So here we assume that parents choose not only their consumption, which determines their utility, but also the number of children and education of each child, denoted by E. And the utility function of parents is given by this utility function, where consumption, number of children and education shows up in a logarithmic manner. So that's for analytical tractability. So we have a concave utility function in all of these components. Utility increases with consumption, but at a diminishing rate. It increases with fertility, but at a diminishing rate, and the weight of fertility is denoted by alpha. And it increases with education of each children due to a warm glow motive of giving, also in a concave manner, and the weight on education is eta. Now these utility weights, alpha and eta, have to be in between 0 and 1. The reason is that implicitly the one on consumption is equal to 1, and by a hierarchy of needs argument you want to ensure that you don't starve before you think about having children and educating your children, and by the same argument alpha needs to be greater than eta, because otherwise you would want to have education for children that you do not have at all. So if you solve the problem. So the problem is only well defined if alpha is greater than eta, and then we would have a positive population growth rate n. Now individual human capital is a function of education expenditures of the parents. So individual human capital of the children at time t is a function of what parents spend in period t minus 1 on education. The wage rate is denoted by WT, and the costs of children are modeled as foregone wages of parents due to not being able to work when they have children for a certain amount of time. Now, assuming that each child requires psi units of parental time and normalizing the time endowment of the parents to 1, then we would get the budget constraint that we have here, where we have the wage rate multiplied by the individual human capital level of parents. Now that would be the wage if they supplied their whole available time on the labor market. But since each child reduces the time that parents have to supply on the labor market, we subtract from their time endowment psi multiplied by the number of children here from the time endowment, and the remaining time is what parents can spend on the labor market. This is a convenient way of modeling child costs, and it leads to the situation that fertility in the end is constant and does not depend on the wage rate. And this is plausible in a sense, because otherwise, if fertility depended on the wage rate, it would either increase with the wages and go up to the upper bound of fecundity, basically, and that's not what we observe, or it would go down indefinitely and converge to 0, and that's also not what we observe. So in rich countries we observe a rather constant fertility rate for a changing wage income. So on the left hand side of the budget constraint we would have wage income of households after adjusting for the time they cannot spend supplying their work on the labor market because children take time to raise. Now the income that they earn can be spent on consumption or on educating the children, where psi is the price of education by assumption, E is the amount of education that I provide each child with, and N is the number of children. So multiplying the education expenditures per child with the number of children and the price of education gives the total expenditures of the household for education. So that means total outlays of the household for consumption and education have to be equal to total wage income after taking into account that raising children costs parental time. Now we solve this household's utility maximization problem by first setting up the Lagrangian function, that is the utility function as on the previous slide, plus the Lagrange multiplier times the budget constraint, where all the terms are brought to one side. And then we have three necessary first order conditions for the three choice variables: consumption, fertility, and education. Now for consumption it's easy, taking the derivative of the logarithm of consumption with respect to consumption is 1 over consumption. And here we only have, so this term drops out, this term drops out. Here we don't have consumption, so the first term drops out, the last term also drops out. But here we have consumption, so we have minus the Lagrangian multiplier that remains by taking the derivative. So if we bring it to the right hand side, we have the first order condition. With respect to fertility, it's a little bit trickier. So we have alpha divided by n if we take the derivative of this term with respect to the fertility rate n. This drops out, but here we also have n, so we have minus lambda t times wt times ht times psi. And then we also have another term here that contains the fertility rate, so we have another minus lambda times psi times e. Now if we bring everything on one side, on the left hand side, except for the Lagrange multiplier, then the resulting equation that we get is this equation number 2 here, so the second first order condition. And finally we also take the derivative with respect to education. Then we would have eta over e, education, here. And here education shows up in the last term, so we would also get minus lambda times psi times n. Again, if we isolate everything on the left hand side except for the Lagrange multiplier, we get equation number 3. So now we have 3 equations in 4 unknowns, because we have the 3 choice variables and the Lagrange multiplier, but we have a 4th equation, namely the budget constraint, that we can use to solve for the 4 unknown variables. Now, in doing so, we follow the next steps. We take equations 2 and 3 together, set them equal to each other, and from this we can isolate the expression, the equilibrium expression or optimal expression for education, where we see that education increases with income. So if households earn more income, they would want to invest more in their children's education, and it depends on the parameters that we will interpret later on. Then from equations 1, 3 and 4 we can get an expression for consumption, and in this case consumption still depends on the fertility rate, which is also a choice variable, so we want to get rid of this. In order to do so, we plug the expression that we had for education from the previous slide and the expression that we have here for consumption into the budget constraint. And if we do so, we can then simplify and derive an expression for the optimal fertility rate. And the optimal fertility rate then only depends on parameters, so that's already the solution that we have for optimal fertility. We will interpret this in a second. Now we can plug this back into equation 5, into the fertility expression here, such that we can compute equilibrium consumption, optimal consumption expenditures, and we see they also increase with income of households. And we see that education expenditures and consumption both increase with income of households, but fertility stays constant. And the reason is that we modeled the costs of fertility as foregone wages of the parents, and it's also a desirable property for fertility because we know that fertility stays rather constant for increasing incomes, or at least it does not increase with incomes without bound. While for consumption usually increases with income, and also education expenditures tend to increase with income. So the outcome of this utility maximization problem is actually reasonable. Now we summarize here on the next slide again the solution to this optimization problem in terms of optimal consumption, optimal fertility, and optimal education of adults. And now what is important is the interpretation in terms of the quality-quantity trade-off effect. So if parents want to have more children, that would mean if they have a higher weight on children in the utility function, so alpha is higher, then we observe that fertility would be higher, but education expenditures would actually be lower. And it can be shown that fertility will be higher, despite the fact that alpha also shows up in the denominator of the expression for fertility. So if parents want to have more children, they raise fertility but decrease education expenditures per child. Now the reverse holds true if parents want to have better educated children. in this case, they would have a greater weight on education in their utility function. So eta would be higher, ceteris paribus. Now, if eta is higher, we see here that fertility decreases, but education expenditures increase. So we have it in the denominator with a minus sign, so that's even reinforced this increase, and we see directly that we have this quality-quantity trade-off also in this case. And finally, if the time costs of children rise, so if psi is higher, then fertility itself decreases, but education investments increase. So this, all of these aspects are related to the quality-quantity trade-off, and this quality-quantity trade-off is also supported by empirical evidence within different families usually, but also across countries and different states when the interrelations between education and fertility are estimated. And this inverse relation between education and fertility is also well known from the family economics literature. So it's firmly grounded in theory, and it's also supported by empirical evidence. In the next step, we use the result from the household optimization problem to solve the model for the macroeconomic equilibrium. And the necessary step in doing so is that we need to model how human capital is actually produced out of education expenditures of parents. And we assume here that human capital is quote unquote produced by teachers who are undergoing wage rate W. Now we can determine equilibrium on the education sector basically, where first of all we compute education expenditures. So education expenditures of households, they are the price that households pay for education, multiplied by education per child, multiplied by the number of children. So that would be total household expenditures on education, and then we multiply it by the number of households and we get total education expenditures in the economy. Now we can plug in the expression that we derived for education ET, then psi drops out, so that's what we see here. If we plug in ET, psi drops out because it's here in the denominator, and we have here the income of households, and we do not substitute out fertility here because we will see later on that not doing so leads to a very intuitive equation that we can interpret rather easily. Now that's total education expenditures. Now we write down basically what is done with these expenditures. These expenditures are used to hire teachers, and we denote the number of teachers by LET in the economy. Then we can derive or write down the wage bill in the education sector quite easily because teachers earn the going wage rate and their human capital is HT. So what we have to pay the teachers is this expression here. Now we can set these two expressions equal to each other because education expenditures have to be equal to the aggregate cost of education when we employ LET teachers. And from this we can then derive equilibrium employment of teachers in the education sector. So we set these two expressions equal to each other, and in principle we could then determine the number of teachers when we still had NT and LT on the right hand side. We could also substitute out for fertility and explicitly solve for the fraction of teachers in the economy. But what we are actually interested in is the number of teachers per pupil. And what we have here, NT times LT, is the number of children in the economy. And the number of children is basically what LET teachers want to educate. So we can derive the teacher-pupil ratio here from this expression that only depends on parameters. And that's what we need on the next slide when we derive the accumulation equation for individual human capital. In this next step, we assume that the human capital of children increases with education resources that are spent on each child, so it increases with the teacher-pupil ratio. And we denote the productivity of teachers in producing human capital of children by kappa. Now, recall that the human capital level of teachers is HT. Now we can write down a dynamic equation for the evolution of individual human capital, then individual human capital in time t plus 1 would be the pupil-teacher ratio multiplied by the productivity of teachers in producing human capital, and that is kappa, the inherent productivity, multiplied by the human capital level of teachers, ht. And then we can write down with this the accumulation equation for aggregate human capital, uppercase ht plus 1, which is then equal to lowercase ht plus 1, the human capital of each child, multiplied by the number of children, which is the fertility rate, multiplied by the number of parents in the previous period. And now for this human capital accumulation equation, we plug in the expression that we have here for human capital at time t plus 1, that's this expression. And we plug in the expression that we've derived for the optimal fertility rate in the household optimization problem, that's this expression here. And then we still have lowercase ht from this expression here and the population size from this expression here, but the definition of ht times lt is that it is the aggregate human capital stock. And then we see alpha minus eta drops out here, psi drops out here, and what remains is eta kappa over 1 plus alpha times ht. So we have an accumulation equation for the aggregate human capital stock, from which we can derive the growth factor of aggregate human capital. And that's what we need to solve for the growth rate of per capita GDP, as we've seen previously. Now, if we solve for the growth factor of human capital, we bring ht to the left-hand side, then we have the growth factor of aggregate human capital on the left-hand side, and we have this parameter ratio from here on the right-hand side. Now, if we subtract 1, we get the growth rate of human capital on the aggregate human capital on the left-hand side. And now what we see is that the growth rate of aggregate human capital increases with eta, where you remember eta was the weight on education in parental utility. So if eta increases, households increase education expenditures per child, but they decrease the number of children. So the number of children, the fertility rate, decreases in eta. Now what this whole thing tells us is that the negative effect of the decrease in fertility that is associated with this increase in eta on aggregate human capital accumulation is overcompensated by the positive effect of eta on education expenditures. And that means aggregate human capital growth increases despite the fact that fertility decreases with this parameter change. And a similar effect holds true if we increase alpha. So if alpha increases, we have a decrease in aggregate human capital accumulation, but an increase in fertility actually. And the final step is now to use these results in the growth rate of per capita GDP. We've seen previously the growth rate of per capita GDP is this parameter cluster lambda over 1 minus phi times the growth rate of aggregate human capital. Now this parameter cluster doesn't need to concern us because we've already seen the interpretation in the semi-endogenous growth model, and this interpretation carries over to this semi-endogenous growth model with the quality-quantity trade-off. So it is constant, but what we observe, and this is crucial, per capita GDP growth increases if the weight of parents on education of their children increases, but per capita GDP growth decreases if the parental weight in the utility function on the number of children increases. So in this case, we would have that education expenditures per child go up, but fertility goes down, and aggregate per capita GDP growth goes up. So we have an inverse relation between per capita GDP growth and fertility, as we've seen it in the data in the scatter plot that I've shown at the end of the chapter on semi-endogenous growth models. And the same holds true if we vary the parameter alpha. If alpha increases, then the number of children goes up, but per capita GDP growth goes down. So this model and the results of this model would be fully consistent with what we see in the data, the inverse relationship between fertility and economic growth. So to summarize, in this chapter we have seen a growth model that can account for the negative relationship between fertility and economic growth by means of including the quality-quantity trade-off between the number of children and educating children in the household's decision problem. Now, in addition to the effect that we just discussed, there is another effect that would show up as a level effect actually, and that is that if the number of children increases, then the time that parents spend on the labor market would decrease. So this is basically an effect that would lead to a shift in labor force participation of the parents, and that does not show up in the long run growth rate, but it would shift to lead to a level shift in per capita GDP that goes further into the direction of a negative association between fertility and economic growth, as we've talked about it. So this would rather reinforce the result that fertility and income are negatively related. And there are also other mechanisms that could complement the channel that is described in this chapter. For example, if health were another form of human capital, then we might also have quality-quantity effects with respect to health of children. Then we would have the neoclassical capital delusion effect on top of the effects that we presented here in this chapter. And we could also have effects of the population structure, the so-called demographic dividend. Namely, if the number of children decreases, then what happens initially is that until these children enter the workforce, the number of dependents in the economy actually decreases. And this can have strong economic growth effects, and it had strong growth effects, particularly in Southeast Asian countries, and also, for example, in Ireland, where researchers have shown that the decrease in the youth cohort actually, that led to an increase in the ratio of the working age population to the dependent population, actually freed resources that could then have been spent on education and for example, public infrastructure and so on and so forth. And the countries that did this successfully earned a demographic dividend in terms of economic growth. Now this concludes this chapter, and the next chapters will deal with other aspects related to human capital accumulation and economic growth.